Okay, so did I get that right? So, so that's a sample graph, and we want to send, say, oil from the source vertex S to the sink vertex T. Okay, and the way the problem is formulated, you have edge capacities, right? So each edge represents a pipeline, and you want to say what is the capacity of the pipeline, and so that's marked. So you have some pipelines that can carry 1 unit, and others that can carry maybe 10 units, and so you have a range in between that. And the other implicit constraint that we all understand whenever we talk about flows is that it cannot accumulate anywhere, right? So for all intermediate vertices, right? So the amount that comes in should be the amount that goes out. Okay, so that's the constraint, and then you can immediately see that okay, this is a linear programming problem, right? So you have edge capacity constraints, right? So you have variables. You have a variable corresponding to the flow on each edge, right? Because ultimately, what you want to find out is how do I not only you want to know what is the maximum I can push. I also want to know how should the pipelines, how much should I send on each of the pipelines, okay, in order for me to achieve this bound, okay? So the variables you want to set this up as a linear programming problem are the amount of flows that are going to be on each edge, right? So you have, if there are n edges in the graph, then for each of those edges you're going to introduce a variable in the linear programming problem, okay? Secondly, you have these flow constraints, which basically say nothing should accumulate at any vertex. So you're going to say, the kind of constraints you're going to add here are, you would say, for instance, x SA plus x BA, okay, equals x AB, right? So that says that the flow that comes into A from these two edges should be the same as the flow that goes out, right? So that is basically this equation, right? So that's, for each of those vertices, you will have equations of the form. Okay, so those are the additional constraints. So these are equality constraints as opposed to, say, inequality constraints. Okay, but the capacity constraints are inequality constraints. So now that you have a bunch of linear constraints, right, and you have an optimization function, which is that you want to maximize the amount that flows out of S or flows into T, right? The two are equal, right? Obviously, if we are going to enforce this property of conservation at each intermediate vertex, well, that means the conservation is going to be there at between the source and sink as well. So you can say my objective function is to maximize the flow, which is to say that you want to, so your objective in the linear programming problem is maximize x SA plus x SB plus x SC, right? So that's your objective that you want to maximize that, and then there are a bunch of constraints, and of course now you know, okay, the linear programmer linear programming solver is going to come up with a solution for it, right? So of course if that's all there is, then we would study this as a topic, okay? But the reason why we want to look at it as a linear programming problem is to sort of understand how simplex method is going to solve this problem, okay? And we want to sort of understand how it works, and then we want to abstract from that and then design a direct algorithm which is more efficient, okay? So this is our goal. And the reason why we study powerful algorithms is because they can allow us to solve a wide range of problems, okay? But of course, the downside of using a very powerful technique is that very often it may not be that efficient, okay? Okay, so it can maybe solve a very general class of problems, but the downside often is that it doesn't solve the problems efficiently. But then what we can do is we can use this technique to study the problem, understand what solution it comes up with, and trace its steps, figure out exactly what it is doing, right? And then say, okay, now that I understand how to go about solving this problem in general, okay, can I make use of special structure of the problem that I have in hand? So for instance, this is not a general problem involving a bunch of variables and constraints on them. It's a problem involving graphs and very nice properties such as conservation. Okay, so maybe we can make use of that and understand that in fact, from that we can learn how to come up with a better algorithm. That's basically what we're trying to do. And I want you to sort of think about how we study shortest path algorithms, right? So we said, okay, if you want to do shortest path in general graphs, you in general will end up with recursive equations, right? With dynamic programming problems where the equations are recursive, and then we said, okay, there's a general technique for dealing with recursive equations, which is iterative solution, and we said, okay, let's go through those iterative solution technique, and that tells us how to solve the problem, and then we can step back and say, okay, here is where this technique is not very efficient, but I can make these changes to make it efficient, and then I have algorithms that are customized for shortest path, but the way we got there is by the insight we get from applying a more general technique. The same thing we're trying to do here. We're trying to take the more general linear programming technique and apply it to solve this problem, and then from there we'll see how we can make this all efficient. Okay, so how does simplex method solve the problem? Okay, so we know simplex method starts at the origin. Okay, so again, since we said the variables represent flows on each of the edges, right? So origin means everything is 0, right? So therefore, the starting point for the simplex is 0 flow. Okay, and then it moves to the next corner. Okay, now I'm saying that the next corner means pushing maximum flow through one of the paths. Okay, so why is it not, let's say, just increasing the flow on one edge? Why is it on a path? Can you tell me why it's not an edge and it's a path?
Further down the flow can be along the
We have to maximize the path. We have to
path flow.
No, again, so let me make the question a little bit more clear, because I think you are giving me an answer which is getting there, but okay, so the point is that simplex is a step-by-step solution, right? So going to go from the origin to the next vertex, right? And then the next vertex and so on. Ultimately, you'll get to the right solution, okay? So what we are trying to understand is, okay, when it makes the first step, what does it correspond to? Okay? Now, if you somebody's first guess would be, okay, maybe the first vertex corresponds to setting, one variable to some value and everything else, leaving everything else as 0. Okay? But what is being said here is that no, that's not what it is. It is actually finding one path and setting a flow on that path. And I wanted to tell me why it's not an edge and it is a path.
The shortest characteristic edge actually will decide the flow because of conservation of flow. It will decide the flow through each of the edges in the path. So we need to decide that path so that we know the flow from each edge.
Okay, let's try to be to the point. Okay, so my question is, why is it not the case that it is setting, let's say, x SA equal to 3 and everything else 0?
When we decide the path, right, so SA, the flow to SA may change. That's based on the path that we decide from SA.
But I'm not talking about the finally, right? I'm talking about the first step that simplex makes. So what is the property of each of the vertices, right? So those vertices are within what we call as a feasible region, right? Okay, so what does that tell you? A feasible region is one where what should hold true?
It's like a boundary condition inequality, so here the inequality should be one path will represent one vertex, because they defines the limit. The graph or the inequality cannot go beyond this vertex point.
Okay, so let's just say that in a different way. Yeah, go ahead. Right, so the point is that that's exactly the point, right? So each of those vertices are within the feasible region, right? What does that mean? That means all of the constraints we have are satisfied, right? So we never bother to do things outside the feasible region, right? We are always inside the feasible region. The only thing that is changing is the value of the quantity that we are trying to maximize, right? The objective function value might change as we move from vertex to vertex. But the condition that all of the constraints are satisfied is always true, okay? And in particular, there is this flow of conservation constraint that always needs to be satisfied, which means that it can't just set xsa equal to 1 because then or xsa equal to 3 while leaving b 0, because that will violate the flow, the conservation constraint here, right? So as a result, a solution that satisfies the conservation constraint is going to be a path, correct? A path in which each edge is set to the same value, right? A path in which all of the variables on the path are set to the same value. That way your conservation constraints are satisfied. And of course, there is also this constraint of edge capacity, so each of those values should be set to the minimum of the edge capacity on the path, right? So the first solution that it's going to try is something that is going to correspond to your path, and it's going to set the variables on the path to be such that they correspond to the minimum of the edge capacity. So for instance, it might pick this path and then say, okay, what is the minimum edge capacity? 2, 2, 3. Okay, so that minimum is 2. So it's going to, the first vertex could be that particular value, that particular path with a setting of 2 for every variable. Okay? Of course, we won't know exactly which one is the next one because we haven't even specified in that level of detail how simplex works. So let's take a very simple example, okay, not the big example, that we'll look at that a little bit later. So this is a very simple ST network with just two intermediate vertices, right? And so simplex might pick the SAT path, or it might pick SDT path, okay? So it might pick one of the two, okay? And the next step, of course, is going to pick the combination, okay? And so in the end, it's going to end up with this, where you have one flowing through here and one unit flowing through that path, and so you are able to deliver, send 2 units from S to T, okay? So that's how simplex works, okay? The catch though is, well, it seems that, okay, what happens if you end up, if the first path you select happens to be that, okay? Now you can see that from here, either you go to SABT, or on the right you will go from S to B and then to A and then T, right? So either way, you can see that you can't add any more flows, correct? Because the outgoing capacity of one vertex is exhausted and the incoming capacity of another vertex is exhausted in both cases, right? So you simply cannot add anything more. Unless you change something, there is no way to augment either of these to increase the flow, right? So the way we tend to think, okay, so we sort of made a wrong choice of a path and we are stuck, okay? But of course, if you don't think of it in graph terms, and if you think of it as just a linear programming problem, then it's not the case that you're stuck, right? So the point is that, okay, you are blindly going from one vertex to the next vertex in this feasible region, right? And when you go from one vertex to another vertex, some variables may increase, some variables may decrease, right? So we are not saying that it is always the case, but every variable is increasing, right? So the way simplex works, it's just going from one vertex to the next, and it doesn't care whether the variables increase or decrease in the process. Okay, it only worries about the fact that the objective function itself increases, right? The variables can decrease or increase. So in that sense, what simplex will do, if the first path it picks is this, then what it can do is, the next path it can pick can be one which sets the flow from A to be 0, right? So in this case, xab equals 1 on the left, on the picture on the left, xab, the variable xab is 1. When it goes to the next vertex, it's free to change that to xab equal to 0, right? And this is sort of what we need to do. If we want to think of it as a graph problem, we have to figure out, okay, how do I, allow myself to, take some of these choices back, right? And that's exactly what we are going to understand now. Okay? So, the basic idea is that we are going to construct what is called a residual graph, right? The residual graph is going to have edges representing changes that can be made to the original assignment. Okay? So in this case, right, so let's take the first path. So after the first path, so we will have again okay, the residual graph represents what changes can be made to the flow that you have already assigned. So let's take the flow that you have assigned on the left, right? So the flow from A to S to A can be made to 0, right? So the existing flow is going from S to A, 1 unit is being set, okay? You can change that. So that the change you can make is, okay, to either leave it as it is, which is 0, or you can change it to 1 flowing in the reverse direction, which means that forward 1 and backward 1 will add up to 0, right? So that is how we construct the residual graph. Now, going from S to B, right, the change we can make is 1, because the original edge was of size 1, we can now send, if more, if you want. Same way, okay, so let me maybe use dashed edges to show cases where we are okay. So this is called a residual graph. So you take the original graph and then you pretty much go through the path that you have and then invert every edge on the path over here, okay? And for everything else, you are going to leave the original paths as they are, okay? And that's called a residual graph, and that tells you what are the permissible changes to the existing flow. Okay, so now let's define it. Okay, the residual vertexes, they are basically the same as the original vertices, so there is no change to that. The only thing that's going to change is the edge. Okay, so if an edge is not at full capacity, okay, let's say you have an edge here which is, has a capacity of 3. Let's say if your current assignment is to send 2 units through this, okay, so in the residual graph you will have one edge going forward which says you can add 1 more unit, right, to the forward flow, or you will have a backward edge that says you can take out 2 units of flow that's already taking place. Okay, so the residual graph is typically has 2 edges corresponding to each original edge. Okay, so if it's not at full capacity, there will be a forward edge which represents the leftover capacity of that edge. Okay? And there will be a reverse edge which basically shows the current flow that's already on that edge. So essentially the idea is that, okay, the current flow can be turned off, and that's equivalent to pushing the same amount backwards. Okay, so let's look at it through an example. Okay, so we are back to our nice looking, more complex looking graph. And originally the flow is 0, right? So that we haven't set any flow, which means that the residual graph is going to be basically the same as the original graph, right? Because nothing is flowing on any edge, which means that the leftover capacity is exactly the same as the original capacity of each edge. Okay? And since there is no forward flow, there is not going to be any backward edges representing flow that can be, turned off. Right? So there is no flow, so nothing to be turned off, so there are not going to be any backward edges. Okay? So you have a residual graph which is exactly the same as the original graph. Okay? You can go and check, and if there is any discrepancy, let me know. Okay? Because sometimes these pictures change, and I might not have noticed a small change to some edge. So now what's going to happen is that, okay, once you have the residual graph, what you do is you find a path in the residual graph, okay, and you're going to pick a path and add a flow corresponding to that path. Okay? So again, what we are doing is once we have a basic idea of what the linear programming formulation, and when you formulate it that way, and what simplex does, which is basically adding these paths, let's try to do that directly on the graph. Okay, so we know how to find a path in a graph, right? So we want to find a path from S to T. So we'll find the path, and then we will find what is the minimum capacity of edges along the path, and then we'll send that flow through that path. Okay, so this is what we're going to do repeatedly, and that is this is called Ford-Fulkerson algorithm, right? And that's the algorithm actually simply does this, repeats this. Okay, so find a path, send flow. Okay, and then construct the residual graph. Then find a path in the residual graph, send flow. Okay, and then you keep doing this until there is no longer a path in the graph. Okay, so once there is no longer a path in the residual graph, then you know you are done. There's nothing more you can do. So the first step, so initial assignment is 0 flow on every edge. Okay, and then the residual graph is exactly the same as G, which is what we said. And now we pick a path, and again, we could have picked a different path. So, for instance, going from S to C to E to T. But again, for the purposes of this illustration, let's assume that this complicated long path is the one that was chosen. Okay. The reason why we picked this is because then you will see many more cases where the existing flows are turned off. So those steps are easier to, are illustrated by picking this complicated path first. Okay, so we pick the complicated path, and you go from S to A, and then to D, and then to C, and then E, and then T, and then you look at the capacities, and you see that the minimum is 1, right? So what you're going to do is you're going to send 1 unit of flow from S to T using this path. Okay? So that's what you have done. Now remember the path, because we are going to go to the next slide where we are going to construct the residual graph, right? A residual graph which represents a flow of 1 on the path going from S to A to D to C to E to T, right? So in the residual graph, what's going to happen is that these edges that are on this path are going to change in the residual graph, and everything else is going to be left unchanged, right? Because those edges are not carrying any flow, so their residual capacity will be the same. Okay. So do you have an idea of what is the residual capacity, right? So residual capacity is what is left over given the current flow. Okay, and so that means you can either you may be able to add more, so you'll have a forward edge, or you may be able to turn off an existing flow. Okay, and therefore those two. So each edge is going to have two edges in the residual graph, which represent the change that you can make to the graph. Okay, and once again, let's right. So the edges in the residual graph represent the positive or negative changes that you can make to the flow that's currently taking place, or that has currently been assigned to that edge. Okay, so for each edge, some flow has been currently assigned so far. How can you change it? And you represent that using a pair of edges in the residual graph. And this is what we are going to go do repeatedly. Okay, so now we have the flow on the left, right? So we have picked a flow of 1 unit from S to T. And now we want to compute what is the residual graph. Okay, so what is the residual graph? You can see that. So we were sending 1 unit through here, right? Which means that you can still send 2 more units. So you can see that on the right, there is an edge from S to A, which has a weight of 2, right? So that means you can send 2 more. Now, because we are sending 1 unit in the forward way, we can turn it off, which means that you have to put an edge from A to S that has a weight of 1, right? Okay, so any questions? It's all very clear, right? Ready to take an exam, take a quiz on this? And then look at this, right? So this capacity is 2, and then we have already 1 unit flowing, which means that you can add 1 more unit. So the forward edge is 1, and again the 1 can be turned off, so there's a backward edge of 1. Okay, so you'll see that everywhere where along the path there is a backward edge of 1 unit. Okay, and the forward edge, the capacity has been decremented by 1, right? So that's what you see on the right hand side. Okay, so just look through S to A, and then A to D, and then D to B, D to C, and C to A, and so on, right? So you can see that in the D to C edge, right, there is only a reverse edge, no forward edge, because there is no leftover capacity. Right? So obviously you know that because you pick the minimum, there's always going to be 1 edge on the path, which is going to be at its capacity, and therefore it's going to have only inverted edge. Everything else is going to have both forward and backward edges. Okay? Now we pick another path. Okay? Once again, it could be any path, but let's assume that you are picking the path that goes from S to A, D, E, and T. Okay? And again, you have a directed graph where there are both forward and backward edges, right? So when you pick a path, right, in some cases you might end up picking a backward edge, right? That's what we want, because we want to allow ourselves to recover from quote-unquote mistakes we might have made, right? We might have taken the wrong path, sent flows in some direction that in the final solution turns out to be counterproductive, and then we want to be able to invert that, and that's why we are adding these reverse edges so that we can find paths where things are flowing in the reverse direction. So far in this case, we haven't picked anything that flows in the reverse direction, so all the edges picked in the second path are also going forward. Okay, and once again in that path, if you go from S to A to D to E to T, you'll see that D to E, right, as well as A to D, both of them have only a capacity of 1, right? So the minimum capacity on this path is 1, so you are going to augment the flow by 1 more unit, and that leads you to this picture, right? So now you have 2 units flowing out of S, right? So now we've simply added the first path and the second path. Okay? So recall, right? So the first path is on the left, the second path is on the right, shown in thick letters. So you're going to add 1 unit to the edge S to A, so that's going to become 2. 1 unit to A to D, which means it's going to become 2. and the new path is not adding anything to D to C, so you're only going from D to E, so that's going to have 1, and now you're adding 1 to go from E to T, right? So this is what you're going to see on the left. So you can see that the edge from E to T, as well as the edge from S to A and A to D, those have increased from 1 to 2, and everything else remain the same, right? So that's how, so we have so far a partial flow that's able to send 2 units from S to T, right? Okay, so now once again we construct the residual graph, and you can see once, here, well, we have a capacity 3, so now we have sent 2, which means the forward edge now has only, capacity of 1. And because we are already sending 2, the backward edge has a capacity of 2. Right? So that's what we did. And you can see now that we have 2, right? So in the residual graph, you can see that both these edges, right, are inverted. So they are not going to be usable for sending. You can't send things from D. Let me just say that, okay, these 2 edges, both of them are inverted, okay? And once again, you are going to look for a path, and let's say you point this path, SCET, okay? Now, once again, if you follow that, you will see that the minimum capacity now is 3, right? So you're going to send 3 units through that path. And do that. Okay, so now we're going to add 3, which means that we're going to add 3 here. This will become 4, right? And this will become 5. Okay? So that's the change that happened, right? So the rest of the paths on the left remain the same, the rest of the edges remain the same. Those 3 edges were incremented by 3. Okay? So now we have that existing flow, and once again we compute the residual graph, and you can see that now that we are sending 4 units forward, you can only send 1 more unit forward, right? Similarly, the backward edge is now 4 to denote the fact that in the forward direction you're already sending 4 units. Okay, and once again you find a path, and let's say this time, obviously you can't, now with so many edges reversed, you can see that finding paths is becoming difficult, right? Which is what you would expect. You are already started pushing a fair amount of flow already, and so to find places where you can push additional flow is going to be difficult to find. Okay, so in this case there still exists a path SCEDT, and it uses this edge now in reverse, right? Because if you remember, the original graph has edge going from D to E, right? So now to add flow, what you're finding is that, okay, I have to actually send that flow back through the inverted edge, which means that a previously identified path is being somehow edited, right? So we are editing it, we are changing it in some way so that we can actually send more flow. Okay. So if you look at what is happening, you will see that basically the editing that's being done is that instead of going from D to E and then to T, we would simply go from D directly to T, right? So there's no reason to go from D to E and then to T, right? So you can just go from D to T. That's the editing that will happen. So we add this, and once again you see that the minimum edge capacity on this path is 1, so you can only add 1 unit of flow. And you do that, which means that you're going to add 1 here, 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 and here, which means that in the flow, this is going to become 4, this is going to become 5, this is going to become 0, right? Because originally there was 1 flowing now this way, and now you're going to send 1 that way, which means that this is going to become 0, and then there will be a flow of 1 coming from D to T. Okay? And that's what you should have done in the first place, but anyway, you didn't, and now that we found the algorithm sort of corrected itself, right? Any questions? Okay, so now that is the current flow. Okay, so the current flow no longer uses the path between the edge between D and E. Okay, and you are now sending 6 units out of S, and 6 units are getting to D. Okay, and now you see what is the residual graph. Okay, now the residual graph still has a path from S to T, right? And once again, the minimal edge capacity on the path is 1, so you can send 1 more unit. Okay, and that's going to result in a flow like this, right? So you add that SBD path, and you're setting the flow, and now, well, there is no more path in the residual graph, right? So there's no way to add more flows, okay? And when there is no more path, then you know, okay, then you're done, right? You cannot increase it, okay? Now, how do you know that? Is it possible that somehow you arrived at some place from where you cannot go forward? Okay, what is there any guarantee that this is the best you can do? Right? So we know that, okay, we don't have any way to go forward, right? So that's very clear, because in the residual graph there's no path, so at least the algorithm that we are following is stuck. This is it. It cannot do anything more, right? But that's not the same thing as saying this is the best flow you can achieve, right? So how can we say that this is the best flow that you can achieve? Okay? And that comes from something that we won't prove, but at least we can understand. Okay, so let's look at the picture on the right hand side. Okay, and what is happening there is that we have identified what is called a cut. Okay, which I think is a very intuitive concept, right? Especially if you draw a graph in a pictorial form, cut is very clear. You just, there are things to the left and things to the right, and the source is on the left and the sink is to the right, and you want to say, okay, have I exhausted all of those edges, right? In the sense that am I sending the maximum I can send through that set of edges, right? So if I am, it's clear that there is nothing more I can do, right? Because things have to get from the left to the right, and these are the only edges that go from the left to the right, right? And if they are all at maximum capacity, that's all I can do, right? So now, think about what happens in the residual graph when I'm using an edge at its capacity, right? If I'm using the edge at its capacity, the residual graph, the forward edge will not exist, and the backward graph, the backward edge will be exactly the same as the forward edge weight. Okay? So what's going to happen along this cut is that every edge I'm going to see is going to be going in the reverse direction, right? And it's going to be there's nothing that's going forward. Okay? And because of that, you can say, well, this is really the maximum because there is no way to push anything more, and I don't have to think about the algorithm. I can look at the graph and say, obviously there's no way to push anything more because there are no edges left. Okay, every edge that's there that goes from left to right, the source component to the sink component, I'm using all of those edges at their full capacity, and therefore I cannot possibly send anything more. Okay, and this is what is called the max flow min cut theorem. Right, the size of the maximum flow in a network equals the capacity of the smallest cut. Okay, there are obviously many cuts you can make, right? So the cuts might choose any subset of edges. Well, I should say any subset, but there are many subsets to choose, right? So obviously, if I just said, okay, this is the cut set, well, that's not a cut set, right? So it's just disconnecting two edges. There are still other paths to go from S to T, right? A cut set should, remove every path between S and T, right? So, but there are many choices. I could say, here is a cut set, right? Or here is a cut set, or here is a cut set, right? So there are many places where I can draw a line such that I separate the source from the sink, okay? And the theorem says that you find the particular cut which has minimum capacity for the edges that are crossing across. Okay, so the combined capacity of the edges crossing the cut, if you minimize that, okay, that tells you how much flow you can send, right? Because again, the argument that there is things are to flow from left to right, and I'm pushing all I can through those edges, that is true regardless of which cut we are talking about, and therefore it's quite easy to understand what this max flow min cut theorem says. Okay, so coming back to this, so once again the algorithm terminates when the residual graph, right? You try to find a path from the source to sink in the residual graph, and you don't find it. Well, then you say you're done, and that you have achieved the maximum flow from source to sink. Okay, so how do you find this cut set? Okay, now that we have gone through the algorithm and we find that there is no path, can you think of how we could find this cut set? Right? I mean, pictorially, of course, when you look at it, it's obvious, right? But what would be an algorithm that you can use in order to find this cut set? Take a minute to think and try to answer that question. Okay, and then this is why I have the picture here, so you can relate it. You don't have this answer purely in terms of the residual graph. You can also look at the original graph and think of, okay, what is the property, how do I identify these cut sets? Okay, now, this is the cut set I'm talking about, right? So pictorially, the edges going from A to D, B to D, and S to C form a minimal cut set. My question is, given the residual graph, how would you identify that? Yeah, go ahead.
We start from the source, we see all the vertices that can be reached from it.
Yeah.
Like the other set of vertices, the edges between the first set and the second set, they will be
Right. So that's exactly what we do. We do a depth first search starting from S, okay, and then we find what are all the reachable nodes, right? So clearly we have said we cannot reach T, right? So obviously, that's when we stop. So we reach a set of vertices, right? And then any backward edges coming into the set of nodes that we have explored in the DFS starting from S, okay, those would represent the cut set. Okay, backward edges meaning backward edges in the residual graph, right? Now these backward edges will correspond obviously to forward edges, right? That's why I refer to them as backward edges, because they correspond to original forward edges, but represent the fact that you have sent the maximum flow through them, right? Because if you haven't sent the maximum flow, then in the residual graph there will still be a forward edge, and there will still be a path to go forward, right? And so the depth first search will not stop there. The reason why depth first search stop there is because any outgoing edges are at full capacity, correct? So this is why when you do the depth first search and find all of the nodes that are reachable, and then you look at, okay, what are the edges going out of these components, the original graph, but they are not in the residual graph, right? So in this case, you do the depth first search, you will get to S, A, and B, right? Is that correct? S, A, and B, right? So if you do a depth first search from S, the only nodes you can get to the residual graph are S, A, and B, right? And now, the reason why you cannot go forward from any of these vertices is because every vertex, every edge that was the original graph, right? So out of these, so this edge and this edge, right? All of them are at full capacity. That's why in the residual graph they don't exist. Okay? So by essentially doing a depth first search, finding all the vertices that can be reached, and finding what original edges were there on those vertices that no longer exist in the residual graph, that will give you, those set of edges will tell you what is the cut set. And very clearly that defines an upper bound on what you can set. Okay? Any questions? Okay, so